So let's introduce the log normal distribution, and I'm going to just draw it out for you. It can take on a lot of different shapes, just like the normal distribution can. The log normal distribution is a positively skewed distribution. So it's got a long tail in the higher realm of things. And we'll note that the log normal distribution starts at 0. So our x's are all positive. They don't take on negative values. And our x's are positively skewed. So asymmetrical. Can you all think of some things that might follow a positively skewed distribution? Oh, tell me more. Fruit flies.
So yeah, when I took principles of genetics, we had a fruit fly lab. We would cross different flies. So one would have white eyes, one would have red eyes.
Okay.
We would carry out chi-square analyses of.
So what aspect of a fruit fly do you think would be log normally distributed?
Well, it's very just certain characteristics.
Okay.
Like the type of wings.
Okay. So maybe we could just say fruit fly wing length. I don't know, maybe. Maybe you've got most of them are kind of clustered over here, and then we got some really big fruit fly friends that are just ginormous.
Maybe like salaries.
Say again, salaries. Yeah, I was just going to bring that up. So we talked about skewness in salaries and how we take a median salary versus an average, because we might have some salaries way over here. This could be salaries for the university, right? Over here we have the president's salary, right? And over here we have the, we'll say custodian salary, right? And so there's going to be a really big difference, right? But maybe most people are going to be in this range of salaries. A lot of things in the environment, so river flows and rainfall are skewed like this. We have kind of like, your kind of average rainfall, but then you get that huge storm that comes through, right? Wind speeds. I'm not saying that these all follow a log normal distribution, but they follow a skewed distribution, and they're positive. We don't get negative rainfalls. A lot of other things like things of materials, we could say contaminant concentrations. You get a big rainstorm, you get a big flush of contaminants or something like that. So let's talk about some more properties of the log normal distribution. So if X follows a log normal distribution, then the natural log of X follows a normal distribution. So that's kind of that's why we call it the log normal distribution. So we're going to say, let's say y is equal to, y is equal to the natural log of X. So X is our random variable. X could be rainfall or flow or salaries or something like that. We're going to take the natural log of it. And then we're going to define what we're going to call the parameters for the log normal distribution. So these are kind of some funky parameters. We're going to say mu of y is equal to the expected value of ln of x. Okay, so it's basically the mean of the natural logs of x. And if we had data, we could do this. We could just take the mean. And then we'll say sigma y is just equal to the square root of the variance of ln of x. Or if we do this in R, it's just going to be the standard deviation of R says log of x. By default, log means natural log in R. So the log normal distribution looks like this. Very similar to the normal distribution, but just a little bit different. So sigma y times x. And this is where it can get confusing because we have x in there and we also have these parameters which are based on the natural log of x. And then e to the -1/2 ln of x minus mu of y all over sigma y squared. Very similar to the normal distribution, but we've got terms of x and terms of y, where y is ln of x. So we can use, if we say x is log normally distributed with mu y and sigma y, then we can calculate a z-score and do these probability calculations like we've done up till now. So we could say z is equal to ln of x minus mu y over sigma y. And as long as we know these parameters and we know whatever x value we're interested in, we can just use the normal calculations to calculate probabilities and vice versa. But often we don't have a data set, right? Maybe we have just a mean and a standard deviation of a log of the data. And so there's equations that we can come up with that relates the mean of x to the mean of y, and this standard deviation of x to the standard deviation of y. So the real data versus the logs of the data. And so I'm going to give you these equations, and we'll talk about this a lot more later, but this is called the method of moments, where you are essentially fitting a distribution function to data based on the distribution parameters. So we've already done this with the normal distribution. The normal distribution, we need to calculate the mean and the standard deviation. Those are two parameters. And then we can fit our normal distribution to our data based on that. So here we're doing it with the log normal distribution. And I'm going to give you some of these equations here. I'll note that your book uses different symbols. I don't like those. And so I'm going to give you the ones that I like, which I think are a little more intuitive. And so what we're going to do is we're going to relate sigma y and mu y to sigma x and mu x. We can calculate these directly if we have data. If we have a sample of 100, whatever, we can take the logs of that and get the standard deviation and the mean of the logs. But we might not have data. We might just have these parameters. And so if we just have these parameters of x, then we can calculate the log normal parameters from them. And so I'm going to give you those equations now. So mu of x is equal to exp mu of y plus 1/2 sigma y squared. And then we can use this to solve for mu of y and sigma y. So mu of y is ln of mu of x. It's a blizzard out there. Minus 1/2 sigma y squared. And then sigma y, or sorry, yeah. So sigma x is equal to mu of x. It's a function of mu. Square root e to the sigma y squared minus 1. And then we get sigma y, and often these are the equations that we're interested in because we'll probably start out with a mean and a standard deviation of our x values. We want to calculate the log normal parameters. So square root of ln, this is kind of an awkward one. 1 plus sigma x over mu x squared. And we'll note that sigma over mu is also the coefficient of variation. So maybe you're given a standard deviation and a mean of your data, or maybe you're given a coefficient of variation and you can plug it in there. And then finally, I'll give you the median. There's an equation for the median. So the median of x is equal to e to the mu of y. Mu y. And then the function in R is, so this is the function for a PDF. So log normal PDF. And that's D for density, L norm. And then you plug in some values of X, this would be a vector. So whatever. You just give it some values. You give it mu of y and you give it sigma y. And that is going to allow you to plot it. You could also, there's PL norm, which is the CDF. And then QL norm, which is the quantile function. It gives you Z scores. D. So D for density. And let me just do that. So we'll just come up with some numbers real quick. We've got 3 minutes. I think we can make this happen. Okay, so the example I'm going to post, I think we'll probably just do it in class on Friday. But it's an example of the incubation period for SARS-CoV-2. How long does it take for you to become symptomatic after exposure? And so way back when in 2020, we had that 14-day quarantine period. And that's where this number came from. And so the mean incubation period was, we'll just say mu x was 5.6 days. And then sigma y, so sx, the standard deviation was 2.8 days. And then we need to calculate the u dot y and s dot y. So there's an original data set. They found these variables. Now we can use our equation to do this. So our equation for sy was square root of log 1 plus s dot x over u dot x. And then all of that was squared. You can see R helps you out with those parentheses, and then we'll do sigma x, or sorry, mu x was log of mu dot x minus 1/2 times sigma y. So you have to calculate sigma y first squared. Okay. So I'm going to just go ahead and enter those in, and then I'm going to plot this just so we can see what the distribution looks like. So we're going to say x is just, we'll do a sequence from 0 to, let's do 20 days. And then we're going to do y is equal to 0.01. So that's going to be our step. So now we have that nice vector there. And then I'm going to do y is equal to the PDF DL norm. And then you can see what are the parameters here. So I'm going to give it x, and then our mean log is equal to mu dot y, and then our SD log is equal to s dot y. And then last thing I'm going to do is just plot this. So plot x, y type equals L. And there is my log normal distribution for the incubation period. So that's the PDF of it. So we'll do this example in class on Friday. And we'll calculate some probabilities based on that.